We're starting section 5.7, the substitution method. Now, we've been discussing this fact that antiderivative of a product does not have a specific rule. So eventually we've done at least one method of algebraic manipulation to convert an antiderivative of a product to something else and then compute it. So now there are methods that one method that we're going to basically develop in calculus 2 and one method that we develop in this calculus 1. The one that we're doing here is the substitution method. Substitution method uses the chain rule. And so basically, if you remember, we used the anti-power rule and a few whatever derivative method that we had to find the antiderivative of the functions. And this one is basically the anti-chain rule. But it looks like a lot of times it looks like we're doing the antiderivative of a product or a quotient or so on and so forth. So let's do the first iClicker. iClicker question 1, the substitution method is an integration method which results from reversing which derivative rule? A, power rule, B, the product rule, C, the quotient rule, D, the chain rule. And so you can stop it, but I think you remember that one. D is the answer. Okay, so our first example, example 1, we want to take the antiderivative of 3e to the power 3x dx. I know this antiderivative easily because I know e to the power x is the derivative of e to the power x. So this is going to be that. Now, what function e to the power 3x is antiderivative of? Let's try to see, because I know the derivative of basically the argument of the function have to be the same. So first I try this, and I see that it's going to be 3e to the power 3x. Oh, so it's not e to the 3x, but 3e to the 3x is the one that I'm actually as a derivative of a function. And what function would that be? That would be e to the power 3x. So how I write this is going to be e to the power 3x plus c. So that was my guessing method, and it works in a bunch of different occasions, but not necessarily every time. So substitution method is more generalized version of this that actually it works better. And if you missed part of the process, the substitution will bring it back in. So let's do this in substitution method. So where do we start? First of all, I look at, again, we figured out how we can guess the antiderivative. Now we want to figure out how to basically systematically solve this antiderivative. And not every antiderivative is guessing is easy to do, and this is one that we start with, and usually the one that we start with are easier to do with other methods as well. And so in here, if I'm taking the antiderivative of 3e to the power 3x, I look at e to the power 3x, and I have a feeling that this comes from a composition of two functions. And what would be the inside function? So this looks like I'm starting with e to the power 3x, and it looks like that the inside function is 3x, right? And so I set u equal to 3x as the inside function. And then I have to go back and change things. Well, I set u equal to 3x right there. So that would resolve this part. It becomes u, e to the power u. But what will happen to dx? So what happens is that when you have the composition of the two functions, and then you take the derivative of inside and you plug in the inside, which in this case would be u, then you derivative of outside, and you plug in the inside, and that inside would be u, then you will have the derivative of inside also. So that derivative of inside should show with the rest of the material. What is the rest of the material? That number 3 and dx. And so let's see, what is the derivative of inside? Derivative of inside is 3. And so over here, I'm going to replace 3 dx by du, basically. And so going from here, we go over there. And so what we have is going to be e to the power u du. And that antiderivative I recognize, it's e to the power u plus c. And then remember, we have to plug back in the original u. And so that would be the answer. So again, to evaluate the integral, you rewrite the integral in a simpler form by finding the inner function, which is 3x, replacing the composition, the derivative of the composition with derivative at the inner function, derivative of outside the inner function, by basically removing the inner function and replacing it by u. Then you take the derivative of u, and the du, or the differential of u, is going to be the derivative times dx, and so you replace it. And so when we replace dx, and basically the derivative of inside times dx by du, then we actually will not have dx left in the antiderivative anymore, and then we can actually find the antiderivative of a simpler function, and we replace the inner function, and that would be the end of the solution. So now let's do substitution method for a little bit different type of the problem. Here, evaluate z and sine of z squared dz. We don't have an x in here, we have z instead, and that's fine. So now I know sine of u is the derivative of basically negative cosine of u, and so it looks like over here that this should be the derivative of outside function evaluated at the inside function. So that immediately tells me I should at least try to have u to be z squared. Now the next step is to find the derivative of u with respect to z. What do I get? And that would be 2z, and I see the z over there. I don't see the 2, but constants are okay. Constants are very easily manipulated through the problem solving with antiderivatives. So I do have the part with a variable, I just don't have the constant. So if I write du is going to be 2z dz. Now I divide by that 2 to get z dz. Why? Because I have z here and I have dz here, and I want to replace z dz by something of u, and this makes it possible. So the antiderivative becomes antiderivative of sine of u. See, remember, this was what? So sine of z squared becomes sine of u, and the rest become as du divided by 2. Sine of u, I know how to antiderivative. That would be negative cosine of u. And I have a 1/2. 1/2 would come out of the integral. Let me rewrite it again. So basically, first step is 1/2 comes out of the integral. And you will have sine of u du. So 1/2 and sine of u is going to be negative cosine of u cos c. The very last step is to replace back what function? So negative, and u was z squared plus c. And you can try to see if this is actually the antiderivative or not by taking the derivative and listen to this part. As we discussed, this is reversing the chain rule. So if you start from your result and do a chain rule, you go back to the integrand. And so let's see, if I take the derivative of this, what do I get? I get negative 1/2 sine that derivative of outside evaluated at inside times the derivative of the inside, that's negative, times the derivative of inside, and that would be, you clean it up, and 2 and 2 simplify, negative and negative simplify, and you end up with z sine of z squared. Oh, this is exactly the integrand over here. And the red part is testing to see if you have done it correctly or not. Again, how did we do it? We took the complicated part of the integrand, and we found a function that would basically explain the chain rule that we were doing, and then we did the u substitution in there. Of course, it's not always as simple as seeing the integrand being a chain rule of something, and so we get to that also as well. And okay, so substitution method. The substitution method for indefinite integral of f of x dx is part one. First, finding the appropriate expression gx that appears as part of the integrand. That's the inner function. Two, setting u to be equal to that gx, and then du to be the derivative of that gx dx. Rewriting the integrand in terms of u, and hopefully the new expression will be something easier to integrate. And then when you have finished integrating in terms of u, substitute u by g of x back in the in to write the final answer in terms of x. So one thing out of the warnings is that always include dx or du when you're writing the integral. This is a way to keep track of what the process is standing at, and then never mix the two variables together. Again, the substitution method only works when you have basically trying to reverse the chain rule, and so there is a little bit of a guessing game in there, and sometimes it's not easy even if there was a chain rule involved, it's not easy to see it. And you get a little bit more seasoned as you go along, and you do more problems. Practice is the key. I got here question 2. Evaluate the indefinite integral at 9x plus 7 in parentheses to power 5 dx. And maybe take a short break and try to solve it on your own. Find what you want to replace by u, and then find du as well. Now that we're back, and so the first thing that I notice is this: well, if and a lot of time when we were doing chain rule, we had an expression to a it was the basically generalized power rule, that we had an expression to a power, and now we have an expression to power. And with the chain rule, I knew that the generalized power rule would end up with an expression to a power and the derivative of that expression. Look at the expression that I'm thinking is 9x plus 7, right? And the derivative of that is just the constant. And the constant, even if they're not there, I can always multiply and divide and create them there. So that seems like the way to go. So let's say let's start with u to be 9x plus 7, then du is 9 dx. And so if I want to solve dx, what multiplies the expression to power is going to be 1 over 9 du. And so basically this entire thing becomes 1 over 9 u to power 5 du. This is much simpler. And 1 over 9 comes out of the antiderivative, and then you will have u to power 1 more divided by the new power plus c, which is u to power 6 divided by 54 plus c, and replace it back, and you get the antiderivative of the entire expression 9x plus 7 to power 5. So that was things to notice in does the substitution work. Let's remember this, that it's just the reverse of the chain rule, and when you're computing it, basically what is the chain rule? Chain rule is let's say if I have f of g of x, I will have f prime evaluated gx plus times g prime of x. And so when I'm taking the antiderivative of that side, then I should be ending up with the other side. And we know that all generalized antiderivative always contains that c over here. And so what you're doing in here, again, with the chain rule, you had, you would say this is u. So basically you would, over here, you would have f prime at u times du dx. And so basically what happens over here, you're replacing that by f prime of u and this by du, and that's how we operate in here. This is exactly reversing the order of the chain rule differentiation.